Hello everyone, myself I'm Dr. Soujanya. I'm working as an associate professor in the Department of Mathematics, Marri Laxman Reddy Institute of Technology and Management. Today I'm going to discuss about the concept matrices. In matrices, I'm going to discuss the following concepts like introduction. Later I'll go with elementary transformations of a matrix, echelon form to find the rank of a matrix, normal form to find the rank of a matrix. Then I'll go with Gauss-Jordan method, then homogeneous system of equations, and then I'll discuss non-homogeneous system of equations, Gauss-Seidel and Gauss elimination method. These concepts I'll cover in these lectures. Before going to that, why we have to learn matrix? Why we are using matrices, where we are using matrices in real life scenario? See, now in the present technology, everywhere we are using artificial intelligence. It is totally depends on image processing only. So in image processing, now if you are taking an example, like in some of the companies, they're keeping some scanner in front of entrance door. And after scanning the person, if the person belongs to that company, then only the person has get access to enter into the company. Now, latest technology is running like that. So in all these cases, how the scanner is identifying that the person belongs to the same company, even though they have given the list of persons who is working in that company to that machine, but how it is identifying that he's belong by scanning that person, how it is identifying that he's belong to that company. So internally, what is happening is the logic is, if you are taking any image, that image will be saved in terms of matrices. Here I am taking one example. I have taken some small picture. So I divided this picture into pixels. I consider, see here I am taking some pixels for the picture. So in this picture, how it is taking this picture into a matrix form means, it consider wherever the image is there, it takes that value as 0. Wherever the image is not there in the pixel, that pixel will be represented as 1. So the total image is represented in terms of binary number system 0 and 1. So here I gave that representation. Here I don't have, in this area I don't have any picture. So that's why in this part I'm getting some matrices, some value binary number 1. Wherever I have the picture, here I have the picture. So in this position, here I'm getting zeros. Wherever I'm having the image value, if the pixel has an image value, that value in the matrix they are representing as 0. If there is no image in the pixel, they are taking that one as 1. So like that, every image they'll consider, it will be represented in the form of matrices. So a machine can compare the matrices, and by matching wherever the matrix is matching, or else wherever the ranks of a particular matrix are unique, then it identifies that, and the machine identifies that the person belongs to this company and is giving access to enter into the company. So internal logic is the image will be saved in terms of matrix only. Like that, whatever the scenario we are taking in real life, everything will be related to mathematical logic only. So without mathematics, nothing will be there. So here, I'm taking some small example for matrices. So many applications are there. For your understanding, I'm taking one small example where we are using matrices in real life scenario. Now we'll go to the concept. I told you that initially we'll go with some introduction. So first I'll define what is matrix, how we are taking the matrix. So a matrix is a set of real or complex numbers which will be arranged in the form of number of rows, and each and every row contains number of columns. If we arrange a set of elements, that may be a real number or complex number, if we arrange those elements in a particular pattern like number of rows and columns within some square brackets or curly or normal brackets, that type of form is called matrix. For example, I'm taking some values like Aij, where I is from 1 to m and j is from 1 to n. I have chosen m into n values of the form Aij, and I'm arranging these Aij values in m rows and n columns. Like, I'll take the first row value as A11. Here first one indicates row and second one indicates column number. So second column, first row value is A12. Like that, I'm taking n columns in the first row, A11 to A1n. In the second row, again, I'll take A21, A22, and so on, A2n. Like that, if I'm taking m rows, in the last row, it will be AM1, AM2, and so on, AMN. I'm arranging total m into n values in this way in m rows and n columns within a square brackets or a normal brackets. So this type of arrangement is called as a matrix, and here the order of the matrix is number of rows by number of columns. So I have m rows and I'm taking n columns. The order of the matrix is m by n. Like this, we can arrange a matrix in a systematic way, like in number of rows and number of columns. For suppose if I'm taking some real numbers, so I'm choosing, for your understanding, I'm taking some examples like, I'll taking some integers, an integer matrix of the form, some 1, 2, 3, 4, 5, 6. I'm taking the numbers from 1 to 6, which is arranged in 3 rows, 1, 2, 3, in 3 rows and 2 columns. So the order of the matrix is 3 by 2. Or else we can take complex numbers also. For suppose if you are taking the matrix like 1 plus r, 1 plus I, 1 minus I, some 2 plus 3i, 2 minus 3i. This is also a matrix example with order 2 by 2. Like that you can take either integers or complex numbers or rational numbers, any set of values which will be arranged in the form of m rows and n columns, then within brackets the type of form is called as a matrix. So after this, now you have some idea about how we are taking the matrix. Now you have to know some types of matrices, because in this concept my motive is I have to explain how you have to take the rank of a matrix or how to find the inverse of a matrix. In all those cases, we are taking some special types of matrices. So you have to know what are the special types of matrices. So some of the basic types of matrices are upper triangular matrix. Upper triangular matrix means if all the lower diagonal values are equal to 0, then that type of matrix is called as upper triangular matrix. For suppose if I am taking matrix like some 1, 2, 3, 4, 5, 6, 7, 8, 9. I have chosen a 3 by 3 matrix. Here the diagonal values are, these are your diagonal values, 1, 5, 9 your diagonal values. If all these lower diagonal, below the diagonal values, if these 3 are 0, then we can call such type of matrix is as upper triangular matrix. That means the matrix will be in the form of 1, 2, 3, some 0, 5, 6, 0, 0, 9. So this type of matrix is called as upper triangular. See here all the lower diagonal values are 0. So this is an upper triangular matrix. Similarly, we can take lower triangular matrix also. In lower triangular matrix, again here I will take some matrix, some other example. Lower triangular matrix means all the above diagonal values are equal to 0. That means your matrix will be like 1, 0, 0, some 2, 3, 0, 2, 3, 4, 5. See here, these are the diagonal values, 1, 3, 5 are your diagonal values. Above the diagonal values are all are 0. That means this type of matrix is called as a lower triangular matrix. And we are having some type, identity matrix also. Identity matrix means both lower and upper diagonal values are 0 and the diagonal values are must and should be 1. That type of matrix is called as identity matrix. And some more matrices are symmetric matrix. If the transpose of a matrix is equal to the same matrix, then such matrix is called as symmetric matrix. That means if A equal to A transpose, then we can call the matrix A as symmetric. Skew symmetric means A equal to minus A transpose, then we can call the matrix A as skew symmetric. Singular matrix means if the determinant of the matrix det A is equal to 0, then that matrix is called as singular. Otherwise, it is non-singular. That means the non-zero determinant matrix is always called as non-singular. These are the basic matrices which we are using in this lecture: upper triangular, lower triangular, symmetric, singular and non-singular matrices. Now, before going to the concept of rank, first you have to know how to find the rank using normal definition, actual definition. For that, we need some more basics. So here I'll go with those basics. First one is submatrix. Previously, I have taken some 3 by 3 matrix like some 1, 2, 3, 4, 5, 6, 7, 8, 9. This is a 3 by 3 matrix. If you are neglecting some rows or columns in that matrix, then you will get some other matrix. That matrix is called as submatrix. Submatrix means which is obtained by neglecting some rows or columns in the initial matrix. For suppose in this matrix only, if I neglect the first row and first column, then the matrix 5, 6, 8, 9 is one of the submatrix. Now you can neglect some second row and second column. Then the matrix is 1, 3, 7, 9. This is also one submatrix. Sometimes you can neglect only rows or only columns. Oh, that means if I neglect only third column, then you will get the matrix like 1, 2, 4, 5, 7, 8. This is also a submatrix. So submatrix is obtained by neglecting some rows or columns. So our next concept is minor of a matrix. Minor of a matrix means if you are taking any matrix like 3 by 3, like some 1, 2, 1, 2, 3, 4, 5, 6, 7. For this 3 by 3 matrix, if you are choosing some square matrix like 1, 2, 2, 3, the determinant of this square matrix is called as minor of the matrix. That means the determinant of a submatrix is nothing but the minor of the matrix. And since it is a 2 by 2 matrix, it is a minor of order 2. That means determinant means the minor value is, the determinant is 1 into 3 minus 2 into 2. So 3 minus 4, that is minus 1. So here the minor is minus 1. One of the minor for the matrix is minus 1. Like that, minor is nothing but the determinant of a square submatrix. We can't take rectangular matrix. For square submatrix, if you are taking determinant, that determinant value is called as minor. Now we'll discuss about the rank of a matrix. Here the rank of matrix means, for suppose if I am taking some m by n matrix, and I am choosing some submatrices for m by n, or else I am taking some minors for m by n matrix. If the rank, we can say that the rank of the matrix as R, if up to the R plus 1th order, the minor value must and should be 0. And from rth order, at least there exists one minor value as non-zero, then we can say that the rank of the matrix as R. That means I am taking some 3 by 3 matrix like 1, 2, 3, 4, 5, 6, 7, 8, 9. This is a 3 by 3 matrix. So to find the rank value, you have to go with minors. That means you have to take determinants of submatrices. First, I will take the det of entire matrix. So if you are taking det for this total matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, the determinant formula is, which is equal to 1 into det of 5, 6, 8, 9. Next, minus 2 into det of 4, 6, 7, 9 plus 3 into det of 4, 5, 7, 8. So for example, I'll take one matrix like some 1, 0, 0, 2, 3, 4, 2, 4, 2. To find the rank of this matrix, we have to take minors of square matrices. First, I'll take the minor of the 3 by 3 matrix, the total matrix. So that is what det of 1, 0, 0, 2, 3, 4, 2, 4, 2 is 1 into the determinant of 2 by 2 matrix. We have to take first value, neglect the first row and first column. For the remaining matrix, you take determinant 3, 4, 4, 2. Minus next one is 0 into something. So that is 0 only. 0 into the remaining matrix is 2, 4, 2, 2. And next one plus 0 into, this is 2, 3, 2, 4. Clearly the last two values are equal to 0. So take the det value for the first term only. That is 3 into 2, 6. Minus 4 into 4. So this is 3 into 2 is 6. Minus 4 into 4, 16. Minus 10. So you are getting non-zero value. So wherever you are getting non-zero minor value, the order of that minor is your rank. That means since here the determinant is non-zero and the order of this matrix is 3 by 3. So for this matrix, the rank is equal to 3. For suppose if I am taking another matrix like, I'll take one more matrix like 1, 2, 3, 4, 5, 6, 0, 0, 0. So if you are choosing matrix like this, here you have to take determinant for the 3. First you take the determinant for the 3 by 3 matrix. So that is 1 into the det of, neglect the first row, first column, and the remaining value is 5, 6, 0, 0, minus 2 into, remaining matrix is 4, 6, 0, 0, plus 3 into, the remaining matrix is 4, 5, 0, 0. Since in all the cases, one of the row is 0, so clearly the det value equal to 0. So now here for 3 by 3 minor, we are getting 0 value. That means up to R plus 1th order, you got the minor value as 0. Now you go with rth order. Take 2 by 2 matrix and verify the minor values. I'll take 2 by 2 submatrix. I neglect the last row and last column. Then the remaining matrix is det of 1, 2, 4, 5. So what about this value? This is 1 into 5 minus 4 into 2. So 1 into 5 is 5. minus 4 2s are 8, that is minus 3. We are getting non-zero determinant value. That means the rank of this matrix is the minor of the order 2. So here for this matrix, rank is equal to 2. Like that, you have to calculate the rank value. See, initially I am taking the determinant for the total matrix. If it is non-zero, then you can take the rank of the matrix is the same order. In case of equal to 0, you have to take submatrices and you have to calculate the minors where you are getting non-zero minor. You have to calculate the minor values until you will get non-zero value. Once you got the non-zero value, then you can take the rank as the minor of that order. And here we'll represent the rank as always row of A. It is a Greek letter, row is a Greek letter. We'll represent the rank of the matrix A as row of A. And the rank of null matrix is always 0. Why? Because for null matrix, we can't get any non-zero determinant value. So it is always 0. If your matrix of order m by n, then we can take the rank as the minimum of m comma n. The rank is always must and should be less than or equal to minimum of m comma n. Basing on the order of matrix also, you can expect how much of rank we will get. Previously, you can expect some figures. So here, if a matrix is of order m by n, then the rank of A is must and should be less than or equal to m by n, minimum of m comma n. So here, when you are taking rank for your 3 by 3 matrix by using general definition, we can spend at least maximum we can spend 10 to 15 minutes and you can calculate the value. But your matrix is of order 10 by 10 or 50 by 50. In that case, it is not easy to find the rank value using normal definition. So because of that reason, what we will do is, by using some elementary transformations, you have to convert the given matrix to some special form. And basing on the special form, we can estimate the rank value. So to how we have to convert the matrix to the special form, that first we will learn here. That means you have to know some elementary transformations to convert the matrix to special form. Special form means, I told you some of the matrices, types of matrices previously, like upper triangular, lower triangular, or identity matrix. You can convert the given matrix to any one of these 3 forms. So to convert the matrix to any one of these 3 forms, you have to know some elementary transformations. Here we're applying the elementary transformations for rows and columns only. For example, if I'm taking some matrix like some 1, 2, 3, 4, 5, 6, 7, 8, 9. I have chosen some 3 by 3 matrix. Here I'll give some notations for rows and columns. For each and every row, I'll represent with R, that is R1. Second row, I'll take it as R2. Third row, I'll take it as R3. Next, columns, I'll represent as C1, C2, C3. Always, I will represent rows as Ri, columns as Ci. So now, for first transformation is interchanging of 2 rows. Sometimes to convert the matrix to upper or lower triangular, we can't do the calculation with the existing row. At that time, you have to interchange 2 rows. Like if I'm having 0 here, instead of 1, in the first position you have 0. And I want to convert these 3 values. That means I want to convert the matrix to upper triangular form. So upper triangular form is the lower diagonal values must and should be equal to 0. So you have to equate all these lower diagonal values to 0. So to convert all these lower diagonal values to 0, so for suppose if we want to convert this value 4 or 7, total these 2 values 4 and 7 to 0, then we have only one possibility, that the corresponding value in the first row. By using that value only, you can convert the values to 0. But if it is equal to 0, how can you convert those values to 0? It is not possible to convert that value to 0. So in such cases, you need to get some non-zero value in the first row, first column. To get that non-zero value, what we will do is, you interchange either R2 or R1 or R3 or R1. You can interchange 2 rows. That means R2 double implies R1 or R3 double implies R1. By taking this notation, you will get non-zero row in the first row, first column. For suppose if I am taking this only, R2 double implies R1, then you can take the matrix like, so in place of R1, now you have to write R2. You are interchanging both the rows. So in place of R1, now you have to take R2. Your R2 is 4, 5, 6. R1 is 0, 2, 3. We are not changing third row. Your third row is 7, 8, 9. So now we are getting non-zero value in the first row, first column. By using this non-zero value, you can convert this value to 0 very easily. So like that, Whenever it is not possible to do the row or column operations, there you can interchange two rows or two columns. So that is the first elementary transformation on your matrix, either interchanging of two rows or interchanging of two columns. Next one is, sometimes you have to multiply any row with a non-zero scalar. If I'm having some value, our matrix will be some 2, 3, 2, 2, 4, 6, 1, 2, 3. If I have the matrix like this, see in the second row, all the values are multiple of 2. So you can divide the entire row by 2. For simplicity, to simplify the calculation part, sometimes you can divide the entire row or column with 2. Here I can take R2 gives rise to R2 by 2. The total row you have to divide it by 2. That means you will get the matrix like 2, 3, 2. 2 2s are 2 1s are 2. If you are dividing the total row with 2, here you will get 1, 2, 3, and again you will get 1, 2, 3. See, now both the rows will be same, so you can easily convert one of the row to 0. So like that, whenever the calculation part is very difficult, you are getting more healthy, very high values. In that case, you can divide the entire row or entire column with a common multiple. So that is a second elementary transformation, multiplication of any element of a row of a non-zero scalar. Multiplication, since you can take 1 by 2 as 1 by 2 into R2. You can represent division in terms of multiplication also. That's why I'm simply taking multiplication form. Multiplication of any row or column with a non-zero scalar. Why I'm saying non-zero means, by multiplying with 0, all the values will converge to 0. There is no use in that operation. So for non-zero, with non-zero value only, you have to multiply the row or column. That is the second elementary transformation. Next, your third elementary transformation is, sometimes you have to multiply the rows with a non-zero scalar and you have to add or subtract that row with another row. That is our next third elementary transformation. See the third elementary transformation, multiplying every element of a row with a non-zero scalar and adding to the corresponding element of other row. That means if I am taking the matrix like 1, 2, 3, 4, 5, 6, 7, 8, 9. I am choosing one matrix in this form. Multiply, I want to convert these three values to 0. Lower diagonal matrix, upper triangular matrix. That means you have to convert all the lower diagonal values to 0. For suppose you want to convert this 4 to 0. So what you have to do to convert this 4 to 0, I'll take the corresponding value in the first row. So the corresponding value in the first row is 1. So here if you are having 4, instead of 1, in this place if you are getting 4, then by subtracting 4 minus 4, you will get this value as 0. That means I'll take the row operation like R2 gives rise to, I need to convert this value to 0. So how I am converting that value? Multiply the first row with 4. That means 4 R1. Then you will get 4 here and subtract that row with R2, second row. So 4 R1 minus R2. By doing like this, definitely this row will be converted to, this value will be converted to 0. You forgot about the remaining values in the row. You just focus on the value which you converted to 0 and the corresponding value in the other row. Basing on that only you take the row operation. So here I am choosing the row operation as 4 R1 minus R2. Now what about this value? We are not changing first row. Your first row is 1, 2, 3. We are not changing the third row is also 7, 8, 9. We are changing only second row. How I am changing that row? 4 R1. Multiply the first row with 4. Then this is 4 1s are 4, 4 2s are 8, and here 4 3s are 12. Minus R2. R2 is 4, 5, 6. So by subtracting 4 minus 4, you will get 0. 8 minus 5, you will get 3. 12 minus 6, you will get 6. See, you converted this value to 0. Like that, to convert some values to 0, sometimes you have to multiply either a row or column with a non-zero scalar and add that row or column to another row of column in each and every element. That is a third elementary transformation. Totally, we have seen 3 elementary transformations. First one, interchanging of 2 rows. Second one, multiplying a row with a non-zero scalar. And third one is multiplying a row or column with a non-zero scalar and add or subtract that row with another row. So these are 3 elementary transformations. By using these three elementary transformations only, you can convert the matrix to either upper triangular form or lower triangular form. So when you are converting the matrix to upper or lower triangular form, sometimes you will get special types of two types of rows. That means your row may be a zero row, like you will get the matrix like 2, 3, 0, 0, 2, 2, 0, 0, 0. You may get the matrix in this way. For suppose, when you are applying some row and column operations and you converted the matrix to some special form, you got the final matrix in this way. See here, total all the values in this row are 0. If each and every element in a row is 0, such row is called as a 0 row. In the similar way for column also, if each and every element in a column is 0, such one is that type of column is called as 0 column. If there exists at least one non-zero value in the row, then that row is called as a non-zero row. See the first row, 2 are 0. I have one non-zero value in the first row. At least one non-zero value. Since I have 1 in this row, so this one converts to the non-zero row. Here I have two non-zero values. Here I have two non-zero values. So these two are also non-zero rows. So like that, we are having two types. We will get, when you are converting the matrix to either upper or lower or identity matrix form, you will get two types of rows. One is 0 row, another one is non-zero row. 0 row means each and every element in the row is must and should be 0. Non-zero row means there exists at least one non-zero value in that row. Such rows are called as non-zero rows. So these are the basic concepts, introduction topics to learn about the concepts in this matrices concept. So in the next session, I'll go with the echelon form, how to find the rank of a matrix using echelon form. Thank you.